This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
All right, welcome everyone to ECS 178. This course is concerned with curves and surfaces. The art that is necessary to do what? Why are you taking this class? What is so good about it? Do you know anything about curves and surfaces already? Where might this be necessary to use? In what area, discipline, field? Why do we worry about ways to model complicated curves and surfaces? For what scientific or engineering purposes do we need to do that? Anyone? Physics. For physics?
Sure.
Of course. You need everything for physics. Whenever you want to represent something and make a picture of it.
Biology.
Zoology. To represent a sunflower. Very complicated, right? Will I be talking about that? Maybe, maybe not. Let me give you 3 very important areas where we need to represent geometry very precisely. One area is a fun area. I see that you have Disneyland on your shirt, right? So animation, computer animation. Whenever you watch a Pixar movie, there is very complicated geometry and lots of complicated geometry all over the place, right? How does this creature, this Heimlich guy or whatever, any insect, how does it get into the computer? But it has to be designed, right, by someone. So how do we design these things? How do we represent these things? How do we manipulate them? That's essential for computer animation, right? Computer graphics and then movies, frames, and making creatures move. That's the entertainment. Another very important area is, of course, engineering design. Right? Many of us are engineers. We worry about designing car bodies, engines, aircraft. So, of course, we also need to be able to design very precisely down to the level of a millimeter, sub-millimeter, nanometer now, right, nowadays, geometry for an aircraft. A beautiful, slick design of a Corvette or of a Porsche or of whatever kind of car you drive, right? So that is engineering design, car body and aircraft design. The other thing is physics, of course. You said physics. Why? For physics, well, computational simulation, computer simulation of everything that happens around us is being simulated by computational physicists in the computer. So very important to, well, define the geometry that characterizes a physics experiment, a digital computer physics experiment, precisely. For example, what is the blood flow? Biophysics. The blood flow in my body. If I want to simulate that, I need a very accurate definition of the entire set of veins and arteries in my body. How do I represent that? And then the physicist can come in and come up with equations controlling the flow in these structures. So these are very important ones. Entertainment, engineering, and computational simulation for physics, chemistry, biology, whatever around us. Okay? This course builds on 175 computer graphics. But the focus in this course is not on the photorealistic rendering, but it is on the mathematical underpinnings, how to represent shape, how to manipulate shape, and so forth. Okay? So if you haven't taken 175 yet, you should be able to get by with just drawing lines. Okay? I simplify this a little bit, but you need to know C or C++ or any programming language to make you successful in this class. And you have to learn a little bit of the graphics package, at least to be able to render polygons, polylines, things like that. Okay, so we come to that. Let me go over the syllabus a little bit. So everyone has the syllabus in front of you. And what will we be doing? So we will have 2 lectures every week on Tuesday and Thursday nights. We will meet here. And I would like this to be interactive. Okay, so we will talk to each other. And I will adjust my speed accordingly. There is one really super book underlying this course. It is this book by Gerald Farron. It's called Curves and Surfaces for CAGD. It is really one of the best books in all of computer graphics. Get it. Okay, even if you do not want to specialize in computer graphics, everyone needs to have a copy of this book. It's just very beautiful. And you can use it, whether you are in mathematics and physics and chemistry or in computer graphics. You will always treasure it. There will be 5 assignments in this class. I plan to assign the final grade only based on the programs. Unless for some reason we jointly decide that there should be a final exam, then I will also give a final exam, so we can discuss that. But there will be 5 assignments, and the first 4, I will tell you what to do. And on the 5th assignment, you will educate me and tell me what's cool, okay? So the 5th one, you can already think about something that's cool, that's exciting to you, and I will be happy with anything that you come up with that's exciting to you. Because if it's exciting to you, I will like it, right? Huh? So, 5 programs, and let me introduce my assistant. This is Sohail Shafi'i. Sohail is kind enough to work with you on your assignments, meaning he will take a look at your projects when they are done. Okay, so all the deadlines are in the assignments, and Sohail will set up times when he looks at your program for 5 or 10 minutes and says, this is cool, 100 points, or this is not quite so cool, 95 points. Okay, something like that. So Sohail will take a close look at all of your projects and check them out. I hope to answer all the questions that you have, technical questions, during class. Whenever I'm going too fast or whenever something is not quite clear, you jump in there and you say, Bernd, hey, I didn't quite get this. Can you explain it again? Or use different words. How will this go? Well, grading is straightforward. If you are in the 90 to 100% range, of course you get your A. If you are between 80 and 90, you will get your B and so forth. So you are assured to get those grades at least. But then, of course, if things do not turn out that well, then I will adjust the grading scheme in the end, of course. Programs can be late, of course, but no more than 7 days. If after more than 7 days, Sohail can no longer accept your programs. So, for your own sake, try to be on time whenever you can. And the most important parts are, of course, that all your programs are complete and correct. The interface doesn't have to be super slick. It doesn't matter, right? The important part here is that you understand the mathematics. So I want you to focus on the underlying mathematics and show that the curves that you draw are correct curves and correct surfaces and so forth. So do not spend too much time on the interface design. Focus on doing the math correctly. And then I give you some additional books, which are all cool books. And then there is a tentative course outline. And today I thought I will just go over some of the topics that we will mutually enjoy here. And also I gave you a big list of recommended literature. So there is this one page in there with very small print. And if you want to focus in computer graphics or computer animation or any of these fields related to graphics, this is your little library that you have to build. Okay? If you see yourself specializing in computer animation and you want to land a job with Pixar or ILM or Disney, whatever, you need to read all these books and fully understand all of it. And you need to understand physics completely, because otherwise you cannot simulate the mechanics for animation. All right. So far, so good. Are there any questions? Any issues that we should talk about or questions that you have? You can do the programming on any machine of your choice. You can program on any laptop. You can program on any of the machines in the basement of Kemper Hall. Whatever. The only important thing is that you have to be able to agree on a place where you can demonstrate your programs to Sohail. And that should be in a central location. Okay, Sohail cannot run after you. You have to we meet in Kemper Hall, room so-and-so, and then you have to demonstrate it there. Either you bring your laptop, you bring your machine, or you grab one of the machines in Kemper Hall basement and demonstrate it there. I'm completely flexible there. Also in terms of programming language, it doesn't matter to me whether you use Java, C, C++, whatever. It doesn't matter. You use whatever you are most fluent in. And you can also use any graphics library to do to renderings, okay? Rendering curves, polygons, and so forth. OpenGL, of course, is the library of choice. If you have not done any graphics programming, this is a time to learn that a little bit, how to use a graphics library like OpenGL and make simple line drawings. You have to learn that. Any questions? No questions? Also, I would like to learn your names in this course. So whenever I bring you in and need your help to help me find an answer, then please say who you are. Today is just an overview. I want to give a brief overview of what this class is all about. So it's about curves and surfaces. So when we talk about curves and surfaces, the more important thing is the representation. How do we represent a curve? Okay, so first, welcome. Okay, and now the first thing I would like to talk about is representation. How do we represent curves? Representation. Okay, so there is one form which you know, where we call this line x, and we call this line f, and there is a curve. Then there is another representation where we have the same curve, and we call this again x, and we call this y. And then there is another way to represent the same curve. And it looks like that, again, like this quarter circle. And I give you something else, which I call t, like time, and I give you a piece of that line. So one of these representations is called, if I call this number 1, I call this number 1, I can give this the name f equals square root of 1 minus x squared. That is one way to represent shape or a curve. And this is called an explicit representation. Explicit. If there's something that is called explicit, then there is something that is called implicit. Explicit and implicit. So this next one, let's call it implicit. Okay, do you know about an implicit definition of the circle? How about this? X squared plus y squared is 1. Well, it's the same thing, right? The same creature, written differently. Same thing. So what is here? And x and y are between 1, right? And 0. Here you have to say x is between 0 and 1. Then the other thing is to think of a curve as something that is a deformed straight line. Take a piece of chalk, this piece, and you bend it, you curve it. And that intuition of a curve lends itself to what is called a parametric representation. So this is parametric. Parametric. Okay. So you say this piece of chalk has a length, and this length goes from 0 to 1, unit length, and I deform it. And again, this runs between 1 and 1 here. This is still called x, this is still called y. And now I give this a parametric form. Physicists know about parametric forms, right? What is a parametric representation for the circle?
Just time. Or path.
There is an x depending on t and the y depending on t. Does it help? There are two component functions that describe this. I'm traveling here on this line, and then this line will be deformed and I travel on the circle. Cosine sinus is exactly the trig functions. So maybe I start here. This is x is 1, that cosine is 1 starts out at 1, right? So maybe I start with cosine of t, and the other function is called sine of t. Okay. Doesn't quite work. This was a quarter circle, so therefore this doesn't really go to 1, but it goes only to, a full circle is 2 pi, so this goes from 0 to pi over 2, okay? All right, and when you plug in different values for t, you get points on this curve, parametric curve, right? That's what I travel. In my little car, I would be traveling on this curve. These are representations. There are other representations which are much more intuitive, much better for computer animation, for technical directors at Pixar, right? who all drive very fancy cars. So how do they do that? There is something called polygon-based or polyline-based modeling or representation, corner cutting. There's something called a polygon-based curve, polygon-based representation, rep. How does that come in? Well, are these representations intuitive when you want to model a creature like an insect or a creature like my hand and something like that? What is the function f for my hand? Can you easily write this down? Probably not. No? This is a very simple creature. It's a mathematical ideal which doesn't even exist. Right? This is just a mathematical ideal quarter circle. The hand is much more complicated. It's not a surface at all when you look closely. So these representations are not good for modeling. So when a technical designer, a TD, a technical director, designs something, this is what they would like to do. So I call this the ideas part, okay? So there are some ideas. I would like to sketch a shape. I would like to get something like a shape like that. This is a very complicated shape. Or I would like to get a shape something like this. Okay, very complicated. Very hard to see which function would describe this shape. How do I do that? So there is this polygon-based scheme. You don't need to copy this. This is just ideas, right? So there is something, a designer sketches something which will resemble the curve. I sketch something with a polygon. And this polygon should resemble the shape I want. Intuitive. I don't want to worry about formulas. These are mathematical ideas. I don't care about that. I just sketch a polygon, and the computer produces that. Huh? And you don't worry about the underlying function, right, or the underlying parametrization. So polygon-based modeling. And there's a very fancy name associated with that, and that is called a Bezier curve. Okay, Bezier curve. And this is the most famous curve representation scheme in all of computer graphics. So we will talk about that. And the Bezier curve is based on this principle. You sketch a polygon, and outcome, the computer will generate a smooth curve. So you sketch a polygon, you define a polygon. The polygon is defined by a bunch of points. These points are circles, and they are called B points, B after Bezier. Okay, so there is a first point, B naught, and then there is a last point, Bn, and a curve comes out. Okay, and so why is this good? When you take one of these points and you move them around, the curve will follow. Huh? Because the polygon defines a curve. So whenever you move a point, the curve will follow. That's very cool. You can do this with 4 points, with 5 points, with 20 points, with 100 points. Is it expensive to compute the curve from the points? How do we do that? Don't know yet. So this is one thing. There is something else that we need to talk about. And those are B-splines and rational B-splines. If you can write a computer program that does that, then you're good. But the physicists can do that. F equals ma, that's all. So there's something else that is called B-spline curves. B-spline representations, B-spline representations, B-spline rep. Again, it is a scheme that is based on this idea of sketching a polygon and getting a curve that follows it. But it's slightly different. A Bezier curve works like this. Bezier, Bezier. I give you one polygon, I get you one curve. You give me another polygon, I give you one curve. You give me a polygon, and I give you a curve. Okay? The curve, each curve is controlled by the entire polygon, which is not good. Which is not good. Why not? Because if you create this hand, a model of the hand, and you want to just locally change it, you take one of these control points, right? These points, and you move them. that this movement will change the shape of the entire hand. You don't want that. Okay? You render my nose, my face with the nose in it, and you want to pull the nose. Whenever you pull the nose, you only want to pull the nose and not my cheeks, right? So therefore, you need something else. And that is called B-spline. And that gives you local control. Local control. Okay, so the example I will put here, there is something called an order. An order. An order defines how many control points influence the shape of a curve locally. Order k is 3. And this means 3 points, 3 p and ts influence shape. Influence shape. Okay. So when I draw the resulting curve for the B-spline, 3 points define a shape. These 3 points, the first 4 squares, define the first component of the curve, this component. The next 3 points, 1, 2, 3, define the next component of the curve, namely that one. And the next 3 consecutive points, 1, 2, 3, define the last segment of the curve. Okay? So such a curve consists of multiple pieces. And for example, when you take this guy and you move it around, it will only affect this segment and not that segment. That's local control, right? So that's why this is good. Local geometry control. Okay, cool. Then there are other schemes, many other schemes that I don't have the time to talk about today in the survey. The very important problem that one has to solve oftentimes is a problem of interpolation. Okay. This is in a sense the inverse problem from what I talked about so far. Here I said the user wants to deal with these smooth curves and is manipulating a polygon that defines this whole shape. And all of this is happening in the computer and that's it. Now in the real world, oftentimes you scan geometry and you want to reproduce as accurately as possible the smooth geometry from a scan. Okay, so for computer animation, if you write a game, basketball, football, soccer, whatever, you have your favorite player, and you need to reconstruct his or her body, right, as accurately as possible so the game looks realistic. How do you do that? So there is something called motion tracking or scanning. Okay? So when we do motion tracking, we will put maybe 100 little sensors on my body, and right, locations, markers, and when I move, we would just track where the individual markers are going in space and time. And from all of that, we would reconstruct the shape of my body and how it moves over time, right? The other issue is reverse engineering. If you have an old car body, 55 Corvette or whatever, you scan it in. They are very high-resolution laser scanners, right? And then I scan line by line, and I get 1 million points. All these points are points on the car body, on the Corvette. But all I have is points. That's not good enough for modeling, right? I want to have a smooth, continuous representation. Given points, how do I get a continuous representation? From points to continuum. How do we do that? Well, that's related to the interpolation issue, the interpolation problem. And in its most simple form, it is related to interpolation along the line. Okay? So this is a problem. I give you a bunch of sticks or height values, and I want to interpolate, okay, these values. So I have a bunch of xi locations, xi, and I have a bunch of fi values. And I want to find something that goes with these points or these sticks. That's the problem of interpolation. I have a bunch of xi's, a bunch of fi's, and give me something that passes through. Okay, so this is a function that I want, right? Is that the answer? Would you have drawn that? No, but I'm bizarre, right? So that's why I draw that. So you can also do it this way. Oops. You say, okay, I don't like that, Bernd. I like it to do it this way. You have a bunch of sticks, okay, x, and you want to interpolate, and you say, I like this much better. Okay, is this the way you would have drawn it? Tell me your name again. Alex. Is this the way you would have done it? You don't like this either. Okay, you don't like that, you don't like that. What do you like? Well, okay, I try to be a little bit more accommodating. So Alex says, I like smooth things. Okay? So he says, you give me that, and I want that. You like that better? He likes it better. Why does he like that better? What is better? What is best? All is that this thing, this representation, has to pass through all these bullets, right? All these curves do that. They are all curves. Huh? Do that. Which one is the best? Which one is the best? Best is what? Best? The best is what? So since we have physicists in the class, they always are concerned with energy and minimizing energy. So, just as a side note, there is something called a natural spline, and nature is doing it this way. So therefore it must be best, right? Or and at least energy minimizing. Natural spline. Okay. This is something that is really the best answer to that problem. And the best answer is this. I give you x, I give you these sticks. And then if you were to force a bendable, natural, plastic elastic through these locations, okay, a bendable, plastic, rubber-like material, it would take on a shape, and this shape would minimize something. It would minimize its internal bending energy. And the shape would be completely defined by defining in what ways the piece would be in contact at the endpoints. So if I say it should start out like this and it should end like that, then nature would find the best possible spline going through there. Okay? And in a sense, that is the best. It will look like this. There's only one. And this is called, there is an energy minimizing cubic spline. And this is a word that you will hear more about. What does this thing minimize? This is F. And the definition of energy here is energy is the integral from this first point, which I call x naught, to the last point, which I call xn, from x naught to xn, minimizing the second derivative f prime prime of x squared along x. When you try to solve this, then nature will solve this integral and will give you this unique answer. How does she do that? The way it is. Alright, so this is interpolation. There are other ways to interpolate. Now Alex didn't like the way I interpolated there. Okay? It was too free in a sense, and therefore, having my bizarre imagination running, I created something bizarre. But now you want to constrain it more. You say, Bernd, I do not like this, I want to constrain you a little bit more. So you can also say, I also specify the tangents or the slope. Specify tangents or slopes, in this case. Slopes as well. Slopes in addition. How does the problem look like then? Well, sometimes I want certain things to have certain tangents or slopes at these points where I interpolate. So again, I call this my x-line. I specify or click with my mouse these locations, and I say I want to have certain slopes to be satisfied here. Okay? So this constrains the problem more. One valid answer would be it would look like this, right? Right? You see what I did? I interpolated the height of the sticks, but also these curves have certain slopes at these points. It's nicer, right? The more I constrain the problem, the better the shape, whatever better means. All right, so this is interpolation. Of course, the ultimate problem is I give you 1,000,000 points for my hand, and you want to represent the hand, right? With a smooth continuum. This is just basics, right? But later on, we have to say I have 1,000,000 laser scanned points on my hand. How do I come up with a continuous representation of that? Not just that, but the entire United States and all its buildings scanned from above at 1 millimeter resolution. How many points are those? It's a lot, right? Scanning allows you to do this nowadays. You can scan huge terrains at millimeter resolution. One scan, 1 terabyte. 1,000 scans, terabyte, exabyte, 1 exabyte. How much storage? Can you carry that around? I don't know. I don't even know how to process it. But Suhail worries about that. He does it. Now we also come to the issue of continuity. Continuity. I give you an x-axis, and I give you an f, and I give you a curve. Is this a continuous curve? Yes or no? No, it is not continuous. If it's not continuous, then it's called discontinuous. Okay? So this is discontinuous. Discontinuous. Okay? Or it's also called mathematically C minus 1. Huh? C minus 1. Then if there is a discontinuous way to interpolate, interpolation discontinuous doesn't really make sense. Huh? But anyway, so then there is another way to interpolate continuously. Okay? So this curve is continuous at the breakpoints, right? It doesn't have the same tangent here, right? There's a discontinuity in the slope, but at least the curve is continuous everywhere. Huh? So this is called C0 continuity. We want to do that. And then if things become smoother, and so here the derivative, f prime coming from the left is f prime coming from the right. Huh? And you approach the same point, is not the same, but the position is the same. Now you can also say the slope is the same when you have two segments coming together at a joint point, and there is one unique slope, and they both have the same slope, then that is called C1 continuous. Okay? Same slope, coming from left and right. Same slope. Same slope. And then this is called C1 continuous. So we have to worry about that. Why do we have to worry about that? Because I'm scanning in a certain physical object, and I would like to represent it in the proper way. Sometimes it has to be discontinuous. Sometimes it has to be C0. Sometimes it has to be C1. So that's why we have to worry about that. Sometimes things have to be smooth, should be smooth. You want your car body to look smooth everywhere. Maybe not. Maybe somewhere you want to have some ridge lines, okay, no? For effect. So you do not want to have smoothness everywhere. How do we do that? How can we model a geometry that is smooth pretty much everywhere except at certain lines? How do we do that? That is continuity. The other important thing that we have to talk about is how do we operate on geometry. There are two very important operations or computations we have to be concerned about in geometry, dealing with curves and surfaces, and that is, if I have a robot that is spraying the paint onto the car body, right? Where's the robot arm moving if I'm spraying this tabletop? Then what? The robot is moving its arm in parallel to the table, right? So if I have a definition of a geometry, I need also a definition of an offset. Very important for many applications. Also for machining, numerical machining, whenever you machine something or you're milling something, the milling machine has to run in parallel to the object that you actually want to mill. Okay? So that's why these operations are very important. Operations. I just talk about two of them. One is called offsets. Offset curve. Okay. Again, the application is you have a milling machine running in parallel to the object that you want to mill. So here's a curve. And the offset curve runs in parallel to that curve at a constant distance. So this is an offset, right? This is the offset curve. And this offset is always in normal direction to the original curve. The other important operation we have to worry about is, of course, intersections. Right? You always need to find out when things intersect. Huh? Believe me, you do. When we talk about surfaces, you will see it more clearly. So we need to talk about intersections. Intersections. How do you find intersections between curves? It's probably very time-consuming and not easy, right? I give you two curves, find the intersections. Well, here they are, right? Right? How do you do that? How do you get all of them? How do you find all of them and find them quickly and accurately? Self-intersections of a curve with itself, right? This curve intersects itself. Well, how do you find those? This is important, this operation. So, any questions so far? How do we render these curves? I draw all these things by a bunch of chalk dust on the board. How do we render them in computer graphics? I said all you need to know to render is to render a line. That's really all you need, right? Even though these are smoothing. In the computer world, everything is represented by a bunch of lines. That's it. So, of course, when you render this stuff, you only render a smooth creature by taking a bunch of points, many more points than I use, and you connect all these points by lines, right? Then it looks smooth on the screen, even though it is not when you look closely. Right? This is how you render it, right? Huh? The resolution. So all you need to know is how to render polygons. That's it. No shading, no difficult things to be done. If we are able to operate on curves, we can also operate on surfaces. All right, that's actually where everything gets interesting, right? The curves are just background, right? But we only have to understand really the mathematics for the curves. If you understand the curves really thoroughly, the surfaces come out naturally, okay? It's not a big jump forward. Am I kidding or not? Is it easy to go from a curve to a surface, or what do you think?
It's probably similar.
What is your name again? Tell me.
Joanna.
Joanne?
Yeah.
Is it simple or similar or?
It's probably similar.
The mathematics, right? The mathematics, the underlying structure.
It's probably like extending. Is it like extending a curve
Mm-hmm.
to create a surface?
How do we build a surface from a bunch of points on my hand? How, as a designer, do you design a car body? Where do you start? How do you do that?
Certain lines you use polygons.
Certain lines, polygons, and then you fill in stuff like that, right? So that's the ultimate goal at the end of this course. Maybe 2 or 3 courses down the road, that you write a computer-aided design system, okay? Where you have a bunch of dials, buttons, sliders, input consoles, where you can specify the entire geometry of a car body. How complicated is that thing? It consists of hundreds of thousands of so-called patches. Every little detailed piece on my hand will be a patch, an individual piece of geometry. You need thousands of patches glued together correctly, continuously, to represent geometry as complicated as a hand. Probably. A car body is probably simpler than my hand, depending on how accurately you want to represent it, right? Surfaces. Yes, the mathematical structure is very similar, but rendering is probably more complicated. Right? Now you're in 3D, right? The surface lives in 3D, so all of a sudden you have to kind of like more complicated pictures. but it's easy. So surfaces, if there is a Bezier curve, there is also a Bezier surface, right? So now we talk about surface schemes a little bit, and the things that I will cover in this class. Anyway, I hope that this class will be fun for you and that you learn a little bit. At the end, what comes beyond surfaces? Curves, surfaces, what's the sequence there? Curves, surfaces, volumes, yes, of course. This is not just a surface, it's a volume, right? We don't do that in this class. So, surfaces. So first, there is this Bezier surface and there is this B-spline surface. Logical extensions of the Bezier curve and B-spline curve. So there is a Bezier patch. Okay, it's called a Bezier patch. Again, the idea is I have a little polygon that resembles the shape that I want to represent. So there is something like a control net, it's called. Looks like this. Okay, it's a little tent. And this control polygon or control net, is a two-dimensional structure, right? From a polygon from a polyline to a polygonal representation, we get a patch that is implied by this shape. And when you actually do the mathematics and you evaluate this thing, we talk about this later, you will get a smooth shape lying under this net, control net. Okay, so there's all these lines on this underlying patch. You get the idea, right? So there is this control net, only defined by these four-sided pieces, and there is an entire continuous patch underneath it. Okay? There was a particular structure I used. This patch has how many boundary curves? 1, 2, 3, 4. Is that minimal? No, it's not. I can do one with 3 boundary curves, right? So there is also something called a triangular Bezier patch, which has 3 boundary curves. Okay, so I can do this, of course. Curve, and curve, 3 boundary curves, and the control polygon living above it looks like this. It's a different structure. It's a structure we do not naturally think about. Naturally, we think in terms of rectangles because we are used to rectangle coordinate systems, right? X, Y, right angles, that's it. That's why our brain typically thinks in terms of 4-sided creatures. But the minimal patch is a 3-sided one, of course. Okay, so we have 3-sided things to worry about. Interesting. Again, how do we evaluate that? How do you make a picture of it? How do you make a picture of this patch? When you want to make a picture of this triangulated patch, you use, of course, your ray tracer from 175. You make a ray tracing picture, right? And you can really shade it very nicely, right? Make shading effects and all of that, and shadow and illumination. Right, you can do that? We don't need to do that in this class, okay? I don't want you to write a ray tracer, a high, glossy, cool looking. I'm happy if you render a surface like this by computing a bunch of points on it. And you would connect these points, again, in the normal, natural way, namely little squares, okay? So line drawings again, just lines and little squares that you would use to render it. Okay? And that, when you render it, will look like a net. So here I drew it curved, right? I mean, when you render it, these things will be actually straight lines, right, in your rendering program. That's the way you render it. That's all you need to do. And the higher the resolution, the smoother it will look, of course. But again, you don't need to go beyond line drawings. You need to project it onto the screen, but I forget about that. So now we come to the problem of interpolation, right? Interpolation is the next logical thing. How do we use these schemes to interpolate? How do we interpolate with this stuff? The interpolation problem. For surfaces, how do I do that? What's given there? What's given, and what do I have to construct? What was the case in the 1D case? In the 1D case, I had an x-axis and a bunch of sticks on it, right? And I fit the curve through there. So in the 2D case, what do I have? What is the analog of that? In the 1D case, I started with a line. There's a bunch of sticks, and I fit a curve. So the analog for surfaces would be what? I have a plane, a bunch of sticks coming out of the plane and fitting a surface with that, right? So from 1D, the 1D case was this. I give you a line, I give you a bunch of sticks, and I fit them with lines in a simple way. Huh? What is the analog of that in 2D? In 2D, so I call this f direction, right? And I call this x direction. And so this is this interpolating function that I construct f of x, right? F of x interpolates these endpoints of those sticks. Now the analog in 2D is this. In 2D you have a plane, right? And I call this x and y. And f sticks out in that direction. And I have a bunch of sticks coming out of the plane. Right? That's the input I have there. And I would like to fit a surface with that. What is the analog of that? I connect sticks by lines. I connect sticks by lines. That's what I do here. That's what you do. The analog to that is this. I just connect by lines. Not quite. Going down, going up. Down, here, here, here. Up, down, here. Down, here, down, up, and that, right? So that's my interpolating surface. Right? A very simple one. So each patch here connects 4 neighboring points with using such a quadrilateral. But this is probably not the representation I want if I want a smooth representation of the hand, which doesn't have all these wiggly ridges in there, right? And misbehavior of normals. So here I just have a bunch of quadrilaterals that I constructed. Right? All these things are called a quadrilateral. Quadrilaterals. There's another way of constructing these interpolating surfaces, namely constructing them smoothly. Smooth interpolation in 2D again. So what do I have? I have my plane, x and y. I have my f, and I have a bunch of values sticking out of the plane. So these are these points that I want to interpolate. And one typical approach to do this is to use, as Joanna said, similarly to the 1D case, curves first and then blend in. between. So where can I use curves in this arrangement and then blend in? We know how to do this, right? We know how to do, given a bunch of sticks, give me that. Where can I apply that in the 2D case? And then use that. Yes, successive rows and columns, right? I can do that. So I can apply this curve scheme to these 3 guys, those 3 guys, and those 3 guys. Okay, and then I get an indication of what it looks like in between. Right, so I can do that. And now I can also do it in the x direction, 3 times the curve scheme. That's a cool surface already, right? But still, there's nothing in there. It's empty, right? I have to worry about the representation for the stuff in between 4 curves for each quadrilateral, right? So then you have a situation where you have changed the problem now from 4 points, 4 neighboring points, to be interpolated to the problem of having 4 boundary curves that need to be interpolated in between. Okay? So from the points to a network of curves, and from the network of curves to continuous representations in between the curves. That's what you want. Or that's a rendering of that continuum in between, which doesn't only exist in our mind. How do you do that? So from points, P and TS, to curves, which are these guys, always 4 points on the outside and 4 boundary curves, and from that to a patch. And the patch is fitting the stuff in. Now it gets filled in. Well, we started with individual points that were not even connected. 4 points. 4 points give you 4 curves. 4 curves give you the patch in between. Okay, so how do we do that? This is a natural way we think, right? This is a coordinate system x, 0, 1, 2, 3, 0, 1, 2, 3. Does this apply to my hand? Where's this coordinate system? Is this here on my hand too? This is a very special coordinate system. It doesn't lie on my hand, right? You cannot see that xy system and f on my hand. We need different ways to represent that. So the most likely, more general case is we give up this requirement of always having 4 boundary curves. We just go to triangles. I said triangles are much more general anyway, right? So let's do something that is different. And let's use interpolation with triangle patches. With triangle patches. Okay. Because what did I assume here? I assumed that all these sticks are arranged on a very nice structure, right? 1, 2, 3, 1, 2, 3. And then that's it. It's a 2-dimensional array structure. They don't have to be. I can sample things at any location. So then all of a sudden, if I give up this regularity, I have a situation like this. I have an x, a y, and I just say I have a bunch of locations somewhere here, completely irregularly distributed. No restriction, and there are sticks at these locations. I have sticks at these locations. And now I need to find a surface in between. Where's the surface? I only have sticks. Well, you first have to worry about maybe representing this space in the plane by some meaningful so-called triangulation. So I triangulate this point set, and then I can worry about constructing patches above each of those. So here are the points that I interpolate, right? And above each of these triangles, I construct one of these triangular patches. And then I have to glue them together, right, to get the whole assembly. So another guy would be living here, right? Okay, you get the idea. So we can interpolate with 4-sided things, It's called four-sided and structured. Four-sided and structured. And this is three-sided or triangular and unstructured. So here we have three-sided, 3 edges per patch, right? Three-sided and unstructured. All right. So I said that when Alex wants to design his car body, it requires hundreds of thousands of patches to define it, right? Wherever the patches come together, they have to come together in what way? In a continuous way, right? So continuity is also very much a concern for interpolation of surface data, of course. So we have to worry about putting patches together in a continuous way. So continuity. Okay. So first thing is, I just say C0 continuity. C0 continuity means two patches are coming together, sharing the same position along the shared boundary. Okay. So there is a surface on the left, and this is a coordinate system in x, y, z in 3 space. Okay. There's a surface, and there's a neighboring surface that connects to this surface to the right, if I call this right, and it goes like this. Okay. And they share this same boundary curve. So this curve that exists really twice, coming from the left and coming from the right, but the curve is the same geometrically. But they have different normals here maybe, right? So maybe this one has a normal behavior like this, normals, and they don't have the same normal here, so there's a jump in the normal. So this one has a normal like that. Okay, so that's why it's called C0. Then you now worry about merging things in a smoother way, where the normal is the same, then it becomes C1 continuous. That means it would look like this. There are two patches coming together, but because they are joined smoothly, I don't even see that there are two patches, because they are continuously merged. Okay? So here is this shared boundary curve, but there is the same tangent plane, the same derivative across. Okay? They are joined smoothly. So here, these two patches have same position plus same normal. Same position plus same normal. Normal. Or gradients or slopes. I use these terms vaguely right now, but you can think of it in terms of having the same normal for the time being. Right? So there's the same normal along this shared boundary curve. And here, it's only the position that is the same. Same position only. Okay? Do I only have to worry about continuity between two patches coming together or more? How many patches come together? When I build an entire car body, let's go to the ideas again here. Entire car body, I have a bunch of patches coming together, right? How do I do that? I have a bunch of patches coming together. So if I do that, don't copy this. This is just ideas. So z, y, x. So I have a bunch of patches. So here's a patch. Here's another patch. Here's a patch. Here's a patch. Here's a patch. And I have a patch zoo. Right? All of this should be smooth. So I only talked about the continuity here, right? In this way. Two neighbors. But it's much more complicated, really, right? You have to worry about an entire assembly of patches. So you have to worry about continuity here, here, and where else? There, where they all come together at a corner. Okay? That's a different continuity condition. So you have to worry about the same normal here, but you also have to, everywhere here at these shared boundary curves, but you also have to worry about the same normal for all 5 patches. Right? So there are 5. 1, 2, 3, 4, and here is Mrs. 5. Goes around, and at the center vertex here, you also have to make sure that there is the same tangent plane, the same gradient, the same slope for all 5 patches when they come together. We have to worry about that. So when you write a computer-aided design system where the designer is manipulating happily these hands and so forth, you want to make sure that you never destroy this smoothness, right? The condition that things are merged smoothly. How to build this into a design system. So we have to talk about that. Now, there are 3-sided patches, right? Triangle-based patches. There are 4-sided patches. What comes after 4-sided patches? 3, 4. Give me a number that's higher. 3-sided patches, 4-sided patches, 6-sided patches, right? So, n-sided patches, right? N-sided patches. Why are they needed? Why do we worry about n-sided patches? What is he talking about? Why do we need that? Because geometry requires it. N-sided patches. Okay, so there's a triangle patch, of course, right? A 3-sided one. There's a 4-sided patch. 4. There's a 5-sided patch. And so on. And the 6-sided patch and blah, 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 blah. Why do we need that? Why do we need that? Why do we worry about being able to represent the geometry with different numbers of boundary edges? Why is it necessary? Consider modeling smoothly a cube where you want to have smoothness. Why do we do that? Consider, let's say a suitcase corner, okay? Suitcase corner. Okay. I want to model the corner of something like that, of a cube. But it should not be a corner, not sharp, it should be smooth. How do I do that? Okay, well, if you do that, then you have this top of the cube, right? You have a side of the cube, and you have this right side of the cube right there. If you want to model this, what types of patches do you need? Here you have a 4-sided patch, right? Here you have a smooth. Now you want to round off the edges of this cube. Then you have a 4-sided planar patch here, a 4-sided planar patch here, and now you want to merge these things. So there is empty space right now. This continues. Now you want to blend it. How do you do that? You do that by having a 4-sided curved patch there. 4-sided, right? 1, 2, 3, 4. You have one curved patch here. 1, 2, 3, 4. And you put one here. 1, 2, 3, 4. And what do you see? Can you model everything with just 4-sided ones? No. What is this guy? That's a 3-sided one, right? These n-sided ones, they pop up naturally due to the particular geometry you model. So you have 4-sided ones all over, but then you have the 3-sided guy right there.
Can you always go down to 3-sided?
You can always go to 3-sided. Yes. Now he says, I only want to have a modeling system that uses one type, and therefore the 3-sided type is the most general, because you can take now all the 4-sided guys and break them down into a bunch of 3-sided creatures, yes. So you could write a modeling system where everything is just 3-sided, and then you never need the higher ones. Yeah. But on the higher level thinking, the designer might still think in terms of the higher thing, and the underlying mathematics can be 3-sided, right? So that is that. Continuity. For a curve, that we had an offset curve. For a surface, we will have an offset surface, right? Why again do I need the offset surface? Because the robot is moving in parallel to the car when it's painting the car, right? The robot, the spray can, is moving on a surface which is parallel to the actual car, and precisely parallel at a very constant distance, right? When you are numerically machining with a little milling machine, bzzz, something, then this thing is also moving in parallel to the table, right? At a very precise distance. Sub-millimeter, sub-micrometer precision, right? So how do you do that? So there's also these operations for surfaces we have to worry about. Operations. And number one is offsets, offset surfaces, offsets. And it's simply this. I give you a surface in 3 space, x, y, z. And I want an offset to this. And the offset will be in perpendicular direction to that. So there is an offset surface that lives here. So here was my original surface. And here is the offset surface, the offset. And again, this is in normal direction to the original surface. And in a special distance, constant distance d, everywhere. Now, the other important operation, of course, is called intersections. Why do we need to worry about intersections? Intersections. Intersections. Typically, the individual components of a complicated car body or aircraft design are designed independently. The fuselage and the wing of an aircraft are designed independently by independent designers. Ultimately, all of that has to be merged and comes together, right? And then the wing intersects the fuselage, and you have to compute exactly where is this curve, the intersection curve, between the wing and the fuselage. That's the way it is. So, an example, e.g., fuselage, wing intersection. Okay, so there is a fuselage, a wing that I have somewhere. And the wing is happily intersecting the fuselage piece of an aircraft. Okay, so this is the intersection curve that we need to compute. How do we do that? So I give you 2 patches and they intersect, right? How do you compute the intersection quickly if I give you 2 patches? Right, so you see the 2 patches sticking, right, to each other. How do you get the intersection curve? Probably very difficult to compute. Very difficult. It's already difficult enough to find the intersections of 2 curves, right? Now I'm talking about finding the entire set of points lying on this intersection of 2 surfaces. How do you get that? Do you get it as a bunch of points, or is there an analytical way to actually describe in a closed form, in an equation way, the intersection curve? Probably not. Probably the best you can do is obtain a bunch of points that are close to the actual intersection. And that's it. Or you get a polyline or polygon there, okay, which is close but not the real thing. Why do we need this? We need all of this for manufacturing, for processing, right? So when we have a computer-aided design system, then the designers design the aircraft or the car body. Ultimately, the thing has to be prototyped. It has to come out of a machine. It has to be milled. And for that, we need to do all these additional operations, offset surfaces, intersections, etc., many others. This is an outline of some of the topics we will talk about in this class. Are there any questions or suggestions? What do you want to model for your final project? Any ideas? The first couple of projects will be about a Bezier curve, a B-spline curve, maybe a simple four-sided patch. Ultimately, I would like for you guys to challenge yourself in your fifth project, right? And do something that allows you to model something like a hand, something like a face, something like a car body. Can you do that? Probably not. But doing something that a computer-aided design system should allow you to do, to define a complicated geometry would be cool. And you define yourself how complicated your design system should be. Have a particular design of a particular type of a model in mind. I want to model a finger. I want to model a tire. I want to model a tennis shoe. Whatever. Pick some. What would it take to design something? What does it take to design? These are all the building blocks, right? This class is only talking about the building blocks, how to design something. How do I represent a curve? How do I manipulate a curve? How do I define a surface, manipulate a surface, and so forth? Later on, for a designer, all of this should be completely transparent. All of this, all these formulas, all these concepts should be completely gone at the end of the day. At the end of the day, you would ideally like to be like an artist, right? You go into the holodeck, right? You enter a completely virtual world where you use your hands and you say, give me a chunk of clay, okay? And there's a chunk of clay lying there, popping up, right, from in your virtual world. And then you try to be like, Michelangelo, and you want to sculpt it. And then you just use your hands and you sculpt a chunk of clay or piece of marble, whatever. Okay, and you shape it in real time. There is no formula, there is no control point, there is no polygon. There is just a ray-traced picture of a statue like David or whatever. That's what you want. You want to ultimately have an interface that is so simple that you say, I would like to be able to define something that looks like a cool shape of a Corvette. I would like to prototype that with my hands in a virtual world. I put on my goggles, I see everything in 3D, in stereo, in front of my eyes, in my brain, and I just use my hands directly to shape it, right? An outline of the car body and so forth. I use my fingers to paint it, even it out, like an artist. Now, at some point, a conceptual study or design study of an artist or designer has to become an engineering, precise, right? Design. So then you have to take your initial conceptual design, which is kind of like wiggly and oscillating and not precise. You have to translate that into an engineering representation. For the engineering representation, you have to worry about these things like Bezier representations, B-spline representations. So everything has to be exact, right? Everything has to be down to at least 1/10 of a millimeter precision for a car body, probably even more, right? But this is what we would like to see, right? I would like for you guys to ultimately think of, I would like to be able to design a complicated creature that you see in an ILM movie, Disney movie, Pixar movie, any of these complicated creatures, and you can you see a monster or an insect or whatever in your mind conceptually, and you would like to create that in real time with your hands, right? With a piece of digital clay or digital marble, right? And then you have a bunch of tools, right? Hammers and you sculpt it and you shape it. It's there. And then the computer worries about all these underlying mathematics, these control points, these polygons, the equations. You don't worry about that. Right? So that's what we want to go to. But we are far away from that. Right now we just worry about Bezier curves, right? So how do we do that? Computer-aided design. So this is the type of a system or market or industry that worries about using all these schemes in their huge software. Computer-aided design, or CAD. That's what we are really talking about. So you specify points, you specify curves, you specify surfaces, right? The designer will specify a bunch of points, click, 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 click. System, computer, give me back a curve, okay? I click here, computer gives me back a curve. Huh? Okay, I want to have another curve to the right. I need to specify another curve. Click, 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 click. This is the way the system requires it. I specify points, system gives me back curve. And system gives me back curve. And now I say, okay, I have a left curve, I have a right curve, I want to have a surface in between. I have a click there that says specify left curve, specify right curve, and merge or blend in between. So I say blend, okay, click this curve, click on this one, and click on that one, and give me the surface in between. What is the surface in between? It's a matter of definition. The simplest surface in between is just taking points from here, taking points from there, and connecting them by, well, all we need is lines, right? Connecting them by lines. Okay. It's the beginning of a design, right? Points, curves, surfaces. That's all there is to it. Now I extend this, right? Another one. I want to connect this to another curve here, okay? Give me points. I give you a curve. Specify this as left curve, specify this one as right curve, and I connect corresponding points using this linear or line-based connectivity. Get this, okay? And you build complicated objects, okay? Okay, take this and assume that all of this is symmetric with respect to some. Everything is typically symmetric. Huh? You only have to design half of your aircraft. You only have to design half of your car body because the other half is the same. You just flip it over, right? So, say, okay, now you define a symmetry plane, and say flip everything over, okay? So you say, I click all of this, I click this, have selected it, and then I say, I specify somehow this plane and flip it over, reflect it with this, and then you get the same geometry on the other side, flipped over, okay? No? All right. Then you can say, okay, this is cool. Now I want to rotate it about an axis, right? If you design a rocket, everything is axial, axis symmetric, right? So cars and aircraft are typically symmetric with respect to a plane. Huh? But many flying objects are symmetric with respect to an axis, and then it's an axis of revolution. Huh? So you can do that too. So if you do that, then you say, okay, I specify an axis, I specify some kind of shape, and then I rotate it around. Okay, can do that too. Specify one curve, an axis, and then you rotate everything around. How to do that? So there's a bunch of typical functions that you need in a computer-aided design system. Specifying points, specifying curves, specifying surfaces, and then doing geometrical operations with them. Right? Duplicating them, reflecting them, copying them, and then you want to manipulate them again. Huh? I want to change this shape now. I don't like the shape anymore. I need these points, okay? And then I want to get this curve back. Okay? Or the shape has to change. Alterations. Huh? Specify or define, delete or undo, and modify or insert. Right? The typical operations. Add, delete, modify. So I have to worry about that. And then copying, specifying things, selecting things, copying them, and then a bunch of geometrical operations. Scaling, a small model, a big model. Reflecting, I design half an aircraft and the other one is copied over. Reflecting. Or you need to rotate these things, right? Rotating things around. This is all transformations we talked about in ECS 175. Now, the first project, and I'm coming to my end now here. Lecture number 1 is over. The first project will be about Bezier curves. The first project will become very clear when you go to Friday's discussion section. Suhail will show a movie. Okay, that gives you an idea what is kind of expected from the first project. First project will be very simple, very cool. In the first project, all you will have to do essentially is clicking some points. These points define a polygon, and then this polygon defines a Bezier curve. and you would evaluate points on this curve, a bunch of points, and you would render it by a polyline. Okay? And then assignment 1 does requests a little bit more than that, but this is
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.